Alrighty guys, we're back with writing rational equations today. So all we're going to do is we're going to take a look at how to put some information together to create a rational equation. And so we're going to start off by taking one apart just like we have been. So the first thing I'm going to do here is before I factor, actually I'll look at my horizontal asymptote. I have a situation where the degree of the numerator is the same as the degree of the denominator, so all I do is divide 2x squared by x squared, and I get y equals 2. All right. My vertical asymptote, and if there is a whole, will have to come after I factor. So I'm going to factor the numerator and get 2x minus 1 times x plus 2. The denominator factors into x minus 3 times x plus 2, and right away you can see you've got some factors that cancel here. So everything I do from here on out is going to use this new equation in blue here. I'm going to use 2x minus 1 over x minus 3 for everything else. Alright, so I can see right away my vertical asymptote. I take my denominator, I set my denominator equal to 0, x minus 3 equal to 0. I add 3 to both sides, so I have a vertical asymptote at x equals positive 3. The y value of the whole can be found by plugging in negative 2 to the brand new equation right here. So I would do 2 times negative 2 minus 1 over negative 2 minus 3, and that's going to come out to be negative 2. Hey, look at that. Really? Negative 2? No, it's going to come out to be 1. So I have a whole at negative 2 comma 1. My x-intercepts, I'm going to use the blue equation for that as well. I'm going to set y equal to 0. I have 2x minus 1 over x minus 3. I'll put this over 1 and cross multiply. 0 times x minus 3 is 0. Equals 1 times 2x minus 1 is 2x minus 1. Now here's the deal, you guys. If you've been paying attention before, your x-intercepts always come from the numerator. The denominator is your vertical asymptote. The numerator is your x-intercepts. So think about that when we go down to the bottom here. I'm going to add 1 to both sides. I get 2x equals 1. Divide both sides by 2, and I get x equals 1/2. So I have an x-intercept at 1/2, comma 0. Okay? I could even do a y-intercept here, which isn't up here, but I just want you to see where the y-intercept comes from too. So if I did a y-intercept, if I plug in 0 for x, watch what happens here. 2 times 0 minus 1 over 0 minus 3. The only thing left are these two constants at the end of the function. What's negative 1 divided by negative 3? That's positive 1/3. Okay, look at my original function. I had negative 2 over negative 6. That's positive 1/3. So my y-intercept is always going to be the division of those last two terms. So that's a nice easy point to check later on when you're writing an equation. All right, so let's see what we got here. So where in the equation, so when you're given an equation, where in the equation do you find each of the following? Where do I find the the horizontal asymptotes? I look at the lead coefficients. Look at lead coefficients. All right. Now we have some rules for that. If the degree of the numerator is less than the denominator, it's 0, y equals 0. If the degrees are even in the numerator and denominator, you divide them out. If the degree of the numerator is greater than the denominator, then there is no horizontal asymptote. The vertical asymptote comes directly from the denominator. Okay, so I find the vertical asymptote in the denominator, and these are always factors. Okay, these are always factors. So it might be an x minus 3 like up top. It might be an x plus 2. It could be a 2x minus 7. It could also just be an x. Okay, the whole. I'm going to look for factors that cancel. Look for factors that cancel. Factors that cancel. So if I know I have a hole in the equation, I know I have to see the same factor top and bottom. okay? X-intercepts, this is the numerator, okay? X-intercepts come from factors in the numerator, all right? So my equation that we were working with here, my 2x minus 1 created my x-intercept. It had nothing to do with the x minus 3 in the bottom, all right? So here we go. Let's take a look at how to put one of these together then, all right? So it says for each problem, use the given information to write a rational equation in factored form. Check your work on your graphing calculator. All right, so here we go. First of all, it says P of 3 equals 0. What does that mean? It means I have an x-intercept at x equals 3. Well, if I have an x-intercept at x equals 3, that implies that I had a factor somewhere of x minus 3. Because when I set that equal to 0, it equals 3. So I have an x-intercept of 3, which means I need a factor of 3. And as we said above here, I'll go back up a little bit here, x-intercepts come from factors in the numerator. So right away, since we're doing a polynomial, it talks about p of 3, p of 2. So I'm going to write this as p of x. All right? And let me do this. I'm going to move it over a little bit here. So p of x equals, and then I'm just going to put a division line here. And I know I need a factor of x minus 3. All right? So letter A is checked off. Boom, got that one. Good. P of 2 is not defined. That's the same thing as saying undefined. That means at x equals 2, I am undefined. Well, what does that imply? It implies that I need a factor of x minus 2 in the denominator. My first factor, x minus 3, was in the numerator. So I come over here and I put an x minus 2 in the denominator. That was easy. Done. P has a horizontal asymptote at y equals 1/3. That means that the degree of the numerator has to equal the degree of the denominator. Well, if I look at what I have right now I'm looking at x over x. Those are the same degree. So how do I make it 1/3? I put a 1 in front here and a 3 in front here, and now I've got a 1/3. And by the way, the 1 in front there really doesn't need to be there. Watch this. I'm going to erase that line for a minute, make it a little shorter. Okay? I could also say P of x is simply equal to x minus 3 over 3 times x minus 2. Those two equations are the same thing. It's said to write it in factored form. We don't need to multiply anything out here. Alright, let's try another one here. Alright, so what we got here? We have q of 8 equal to 0. So that means that I have an x-intercept when x is equal to 8. So that implies that I need a factor of x minus 8 in the numerator. Alright, so right away, I'm going to start my equation. This one's talking about q of x, so I'm going to write q of x equals, give myself a division sign, and I need an x minus 8 up here. X minus 8. All right, letter A is done. Q has a hole at x equals 4. Well, that implies that I have a factor of x minus 4 in the numerator and denominator. All right, so I come over here, I put a factor of x minus 4 in the numerator, I put a factor of x minus 4 in the denominator. Now I got a hole. It says that Q has a horizontal asymptote at y equals 0. Well, this implies that the degree of the numerator has to be less than the degree of the denominator. So I go over and I look at my fraction and I see that the degree of my numerator is actually x squared, because if I were to multiply that together, x times x would be x squared, and I only have x on the bottom. So what basically needs to happen now is I need to introduce anything with an x into the bottom that's going to make a higher degree in the bottom than in the top. So what do? Well, what if I just throw an x down here? Now the top is x squared, the bottom is x squared. It's not enough. The degree in the numerator has to be less. So I change my x squared, or change my x to an x squared. I could do that. Now the degree of the bottom is bigger than the degree of the top. I could also do something completely different. I could do q of x equals, so I had an x minus 8 up here, and an x minus 4 up here, and then in the bottom I had an x minus 4. So again, all I'm trying to do is get more x's in the bottom. I could do this. I could do, well, let's put an x plus 1 down in the bottom and an x minus 7 down in the bottom. I can pick any factor I want. I just need to make sure that the degree of the numerator is less than the degree of the denominator. So either one of those would work, red or blue there. All right, next one. Number 3, give an example of a rational function r of x which satisfies the properties. R has a 0 at x equals 2. All right, so let's do this. Let's do r of x. I have a 0 at x equals 2, so that implies in my fraction that I need a factor of x minus 2. All right, letter A is taken care of. R has a whole at x equals 3, so that implies that I need an x minus 3 in the bottom and an x minus 3 in the top. There's my whole, good to go there. R has a vertical asymptote at x equals 4. Now, if you think about it, those x minus 3s, those are removable. If we were graphing this, we would actually remove those, and I should have a vertical asymptote at x equals 4, which means I should see a factor of x minus 4. Now, if I look at what I have right there, if we were to multiply all that together, this would literally be some x squared plus or minus something over some other x squared plus or minus something. Because D says that R has a horizontal asymptote at y equals negative 2/3. So this is what I need to see when I get done, negative 2 over 3. Guess what? All I have to do is put a negative 2 over 3 in the front, and I now have a horizontal asymptote at y equals negative 2/3. And I'm done. Number 4, give an example of a rational function which has no holes, no vertical asymptotes, and a horizontal asymptote at y equals 0. This should be interesting. So let's start off. I'm just going to write it as p of x, and I'm just going to think my way through this. All right, I know that because it has a horizontal asymptote at y equals 0, the degree of the numerator has to be less than the degree of the denominator. There is nothing in here that says I have any x-intercepts, which means I don't even have to have an x in the numerator. So I'm just going to put a 1 up there. Because no holes means no x's in the numerator. No vertical asymptote. So what that means is that I have to have a denominator, okay? Must have a denominator that never equals 0. Gotta have a denominator that never equals 0. Well, how do you do that? You might be thinking, well, just put a 2 in that. But 1/2 is not a rational function. The definition of a rational function says you have to have x's in the denominator. Gotta have a variable down below. So if you think about it, if I just put an x in there, all right, let's see if that works. There's no holes because there's no x up top. Ooh, but I would have a vertical asymptote because if x was equal to 0, I'd be undefined. Okay, well, that's not going to work. Let's try x squared then. All right, still no holes, but unfortunately, vertical asymptote I would still have at 0, because 0 squared would be 0. And my horizontal still works on both of those. So the question is, if I have to have a denominator that never equals 0, then that means my denominator always has to be positive. How do I keep a denominator always positive? Well, squaring stuff keeps it positive. So having an x squared down there is always going to make it positive, but I still have that issue with 0. Okay? I still can't have a 0 down there. So if I know that squaring something keeps it positive, what if I just added, let's say, 2 to that? If I just said x squared plus 2. So I'm supposed to have a vertical asymptote. Let's see if this works. The question is there a number you could plug in for x and add 2 that would be equal to 0? Well, normally to find our vertical asymptotes, we take out the denominator, x plus 2, we set it equal to 0, and we solve it. So I would subtract 2 from both sides. I'd have x squared equals negative 2. I would square root both sides, so the square root of x squared is x. The square root on the right would be plus and minus the square root of negative 2, or root negative 2. This is imaginary, which means there is no place, there is no value of x where that denominator would be equal to 0. I could have said x squared plus 1, I could have said x squared plus 0.05, I could have said x squared plus anything. I can't say x squared minus something. All right? So hopefully that makes sense. Let's keep going and see what else we got here. All right? So now we're given a graph and we want to write a function that would match with the graph here. Okay? So it says use the vertical asymptotes, x-intercepts, and their multiplicities to construct an equation that corresponds to each graph. So here we go. It says also be sure the y-intercept from the graph matches the value given by your equation for x equals 0. Check your work on your graphing calculator. Now I didn't check the other work on my graphing calculator, but you could definitely do that on Desmos.com. All right, so here we go. The first thing I notice is that I have a vertical at x equals negative 4 and a horizontal at y equals 3. All right, so I know I'm going to have a function. I'll call it p of x. And I know that that function is going to have, let's see, an x plus 4 in the denominator. X plus 4 in the denominator. And I've got to have some variable in the numerator with a 3 in the front. Now, again, I could do 3 times x. I could do 3 times x minus 7. I could do 3 times x plus 2. I could do a lot of different stuff that would have the right horizontal and vertical asymptote, but the question is, does it have this x and y intercept at 0, 0? So let's check it out. If I have x plus 2 in there, if I plug in 0, I would get 0 plus 2 is 2, and 0 plus 4 is 4. So I'd end up with 6 over 4. That's 3 halves. That is definitely not what I'm looking at right there. I'm looking at a 0, 0. So when I start to add factors, okay, so I just put in an x minus 7 and x plus 2. When I start to add factors to make stuff work, I always start simple. I start with a plain old x. All right? Now, there's something that I should know about this. There's a reason I should know a little more about that. I have an x-intercept right there at x equals 0. All right? So if my x-intercept is at 0, then that means the factor that creates it has to be x. All right? If I said, for instance, I have an x-intercept at x equals 3, you should know that x minus 3 is the factor, because I would subtract 3 on both sides. But this particular graph has an x-intercept at 0. If I subtract 0 from both sides, it's still x equals 0. And x-intercepts come from the numerator every single time. So if I just toss an x in there, I've got 3x over x plus 4. Let's plug in 0 just to make sure it works. 3 times 0 would be 0. 0 plus 4 would be 4. I get 0 over 4, which is 0. So my y-intercept also works. Okay? Let's check out the next one, number 6. All right, first thing I notice, I've got intercepts, or excuse me, not intercepts, I've got vertical asymptotes, x equals -3, x equals +3. So I'm just going to start my equation while I'm looking at those. P of x equals, give myself a fraction here. I know I need x plus 3 for the vertical asymptote at -3. And I know I need x minus 3 for my vertical asymptote at +3. Okay? My horizontal asymptote is y equals 0. So regardless of what happens here, I've got to have the degree of the numerator less than the degree of the denominator. All right? And I have an x-intercept at 0 again. Ooh, wait a minute, we just got done talking about that. If I have an x-intercept at 0, then there has to be a factor of x right up here. Now let's check it out and see what we have. If I look at my function right now, the degree of the numerator is 1, the degree of the denominator is 2, because x times x is x squared. All right, so that fits with a horizontal asymptote at y equals 0. My factors in the denominator would definitely create the 2 vertical asymptotes, and if we plug in 0 for x, let's do that. We would get 0 times 0 over 3 times -3. That's not 0, that's -9. That's 0 over -9, which means my x-intercept would come out to be 0, 0, which is exactly where it's at on the graph. So I'm probably okay. And I could graph it on Desmos and check it out, but I think we're all right. Go to the next one. All right. So again, first things I'm going to look at, horizontal asymptote, y equals 2. Vertical asymptote, x equals -1. Vertical, x equals 5. So right away I start my equation, p of x. All right, numerator. Here we go. Let me see. Well, let's actually, you know what? I'm going to start with the denominator and see what's happening here. So I've got x plus 1, x minus 5, and at some point I'm probably going to need a 2 in the numerator to get horizontal asymptote at 2. But I'm going to check the other stuff first. Look at this graph here. I have an x-intercept at x equals -4. So x-intercept, x equals -4. And I have another one at x equals 1. Well, if I have an x-intercept at -4, that means I need a factor of x plus 4 in the numerator. If I have an x-intercept at 1, that means I need a factor of x minus 1 in the numerator. Now, look at the degree of the numerator and denominator. The degree on top is squared, the degree on bottom is squared. The only difference is if I divide those, I get y equals 1 from my horizontal asymptote, and I need y equals 2. So guess what? We could throw a 2 up there, and let's check it out. Let's just plug in 0 and see if our y-intercept comes out right in this area here. It looks like it should be about 1.5, right? So I'm going to do a little bit of 2, 0 here. All right, so I'm going to get 2. 0 plus 4 would be 4, so that's times 4. 0 minus 1 would be -1. And then on the bottom, I would get 0 plus 1, which is 1. 0 minus 5, which is -5. Right? And the numerator, 2 times 4 is 8. 8 times -1 is -8. Right? 1 times -5 is -5. That comes out to be positive 8/5, which equals 1 3/5. Does that point on the y-axis look like it could be 1 3/5? Absolutely it does. I'm probably okay. You can graph it on Desmos if you want. Last one here, number 8. Here we go. Vertical, x equals 3. Horizontal, y equals 1. So that implies that the degree of the numerator and denominator right away are going to be equal. Here we go. P of x equals, all right, so the denominator has to have an x minus 3. Right? My numerator is going to be 1, which means I need to have the same number of x's on the top and the bottom with no lead coefficients here. All right, interesting one. it looks to me like we have an x-intercept at 1, so x equals 1 is an x-intercept. And, we have another, this is interesting because we have an x and a y-intercept at x equals 0. So the x equals 0 we've already talked about. So if I have an intercept at x equals 0, that means I need a factor of x in the numerator. I have an x-intercept at 1, which means I need a factor of x minus 1 in the numerator. And now, unfortunately, the degree of my numerator is more than the degree of my denominator. So, how are we going to make this work? We need another x in the denominator. Okay? And based on the shape of the graph, I'm not sure we can pick any old x. All right? Number one, if I just choose x, then I have a hole at x equals 0 instead of an x-intercept at x equals 0. So x all by itself is not going to work. So maybe at this point we go to Desmos and we play a little bit and we see if we can make this work. So let's open up some Desmos. I'm going to pause and get Desmos open here. Okay, so here's my function in Desmos, and you can see that it's the same function that I have there now, and the issue is that I need to have the graph going, well, first of all, I need another factor of something in the denominator, and so you can see that my graph is obviously not going in the right direction here, okay? I do have that vertical asymptote at x equals 3, okay? If we were to zoom out on this a bit, we would have that vertical asymptote, okay? But I need something in the denominator. So we can't do an x, so let's just try, oh, my cursor not go down to the bottom here. Let's see here. There we go. So I'm just gonna try, I don't know, let's try an x plus 1. Let's see what happens here. X plus 1. I still have a vertical asymptote at 3. It's an interesting one. But the curves aren't going in the right direction here either for what we have on our graph. Okay? So, oops. That's what I needed. I forgot my parentheses. Okay, so now I got too much curve. Goodness gracious. Alright, so I got too much curve going on this thing. So, I got to figure out something else. That didn't work. X plus 1 didn't work. I can't do x minus 1 because I create a hole then. So let's try this guy. Let's try, I don't know, how about an x plus 3? No, see, I created another vertical asymptote, didn't I? So what's happening here is every time I put in a new factor in the denominator, I'm creating a second vertical asymptote, which I don't have on my graph. Okay, if you go back and look at that graph, it has one vertical asymptote. So I want you to think about that for a minute. How is it that you create a graph that only has one vertical asymptote, but it has to have an x squared in the bottom? Here's the deal, guys. You have to have the same factor for both. Check it out. I still only have one vertical asymptote. The degree of my numerator and denominator are exactly the same. And I have x-intercepts where it appears I have x-intercepts on my graph. So I need another x minus 3 in the denominator. I could also write that as x times x minus 1 over x minus 3 raised to the second power. Okay? That was a fun one, wasn't it? I know. Little brain buster there. Have fun with the homework.
Take care now. Bye-bye then.